Hi guys, let's look at this problem called minimum penalty. Just a second, let me verify if I'm recording fine. Yeah, okay. So essentially we are given an array of n integers and an integer d, and we need to consider all subarrays with a fixed length of d, and the penalty pertaining to a particular subarray of size d is essentially the number of distinct elements present in the subarray. So, so that's the penalty of a given subarray of length d. We need to report what's the minimum penalty across all the d-sized subarrays in the array, right? So that's the question, and the domain of array A is up till 10 power 6, and as we can see, the sum of n across all the test cases is 5 into 10 power 6. Okay, and yeah, so those are the test cases. And for example, if we see it here, um, let's take this particular test case. So here the size of the array is 6 and the subarray d size is 3. And let's take this particular subarray. So there are two distinct elements, 0 and 1. So this penalty for this is 2. If we slide it one stride to the right, then again the number of distinct elements is 2 for this subarray. So this particular subarray, that is this one, the number of distinct elements is again 2. So up till this point the minimum is 2 because all the three subarrays have been uh, penalized with 2. But the last subarray, that is this one, the one that I have highlighted, that has one distinct element. So this is actually the minimum among all the penalties across all the subarrays. So therefore the answer for this particular test case should be 1, which it is. So hope the problem statement is clear. Um, let's look at how can we solve this problem. Excuse me. So essentially we are given the subarray, and this problem we can solve using uh, simple sliding window approach, wherein for an arbitrary subarray we need to store some information that can tell us how many distinct elements are present in the given subarray. That so this operation it should support uh, number of distinct, right? And what else it should support? Well, for this subarray, if this guy blue guy is the incoming element, that is it needs to slide. When it slides one element to the right, then the blue element will be the incoming element, and therefore the structure should also have a mechanism to quickly um, insert elements, right? um, Whatever the structure be. So but the structure should support answering number of distinct quickly, answering not answering rather applying the operation of insertion quickly. So by quickly I mean it should not be order n, it should be something which is sublinear, root n, log n, or order 1, something like that. If we can support that, then we are good to go. Not just these two, there is one more operation. When we slide, we have to exclude the previous element. uh, I mean the last element of the previous window, and therefore it should support that operation as well, that is the erase operation. So all the three things it should support in sublinear time. Right? So one thing that comes to our mind is data structure like map, ordered map, unordered map. Unordered map is sometimes not very stable. It's unpredictable given to different test cases. So map like structures, frequency table like structures, frequency map, which are balanced binary search trees. These type of structures are good candidate data structure for this particular problem. So that is one way to solve it. But as we see, the number of test cases is very tight. That is, the number of n is at most 5e6. And as we go ahead and look at how do we solve this problem, we will see for a given test case we are overall doing one insertion and one deletion, and therefore across all the test cases we will have order n of these insertion and deletions, and these will take log n time. Right, because that's a map data structure. These operations will take log n time, other than the count of distinct that can be done in order 1. But if we analyze the worst case complexity, all these operations can all be log n. Therefore order n log n pertains to one particular test case. And if we look at n1 log n1 plus n2 log n2, so on and so forth, we can actually make this log terms equal to the given number log 5e6, because all of these will be less than equal to that. And what it will essentially imply is we can aggregate the ni's, the summation of ni's, and I could take this log 5e6 outside. But as you will see, this will be very tight. It might not pass the complexity. So this log 5e6 will be 20 or something like that, right? Or 20 or 22, something like that, which will not pass because this will be very tight. Let's say 1e8 or more than that, right? Greater than that. And the time limit is 1 second, it won't pass. So one approach is we can use a frequency array, and I will show it in the code. And we will clear the frequency array as we go over the algorithm across the test case. So we need not always touch the entire array every time, rather the elements which are impacted. So let's look at this. Um, okay, so we take the array as input, and we initialize the answer to be n plus 1, because this is a minimization problem. The max answer can not exceed n plus 1. In fact, it can never be n plus 1, because the size is anyway bounded by n. Okay, and we for a given index we ask the question, can we insert it? So if we can insert it, we will insert it in a data structure frequency array that is common to all the test cases, and we initialize it with 0, and dist here means count of distinct, right? And just a second, the domain of AI is 1e6, therefore I have taken this to be IE6 plus 5. Yeah, so whatever the incoming element is, we increment it anyway, right? We insert it anyway, and then we ask the question that if the frequency, if the transition of the frequency is from 0 to 1, that means this is a new element. So therefore it increments the distinct count by 1. And when can we remove? Once the elements, so the indices are coming this way, 0, 1, 2, so on, and then there will be d minus 1, and then there will be d. So up till this d minus 1th element, all of them for this, I mean, all these elements will comprise of the first window, right? So we do not remove anything because it still has to uh, grow up to a size of d. So once it has grown up to a size of d, we do not remove it. But the moment it crosses the size of d, that's the first instance where we want to shrink the size and make it d size. So that's what. So for like from d and thereafter, we will remove the last element of the previous subarray. So that is the previous subarray or the previous window, and we remove the contribution from the data structure, and then we ask the question, is the removal transitioning the frequency from 1 to 0? If that is the case, then we need to remove one, like it should decrement the um, distinct elements contribution by 1. So we do that, and then finally we ask the question, is it d-sized? Again, when it is growing, it is never d-sized, so we do not contribute for those subarrays. But the moment it becomes d-sized, that is, it happens at index d minus 1 for the first time, and thereafter for all the elements as well, we contribute the answer. And since we are maintaining the disk count every time consistently, we can that is the contribution for this index, and that's the last contribution. Now notice, as we move along, um, only the elements in the array of the global frequency array are impacted for the incoming AIs, right? Some of them are being like incremented, and some of them are being decremented, and this is invariant. Like whichever are incremented are also getting decremented, except sorry, decremented here, except for the last window. So the last window, um, we have correctly made the answer like contributed to the overall answer, but then we have not cleared the frequencies of the last window elements, right? um, because um, yeah, where is that? Although we have decremented it here, I don't think it should have. Okay, okay, maybe yeah, this is correct. So last time it would have touched the last element, and the last element that would have removed was n minus d minus 1, right? But all the elements which are from n minus d, all the way from n minus d till n minus 1 are still in the frequency array. So we need to explicitly remove them. So that's what we do it here. We decrement them, and yeah, yeah, this was not required actually, because the answer was correctly populated. This was not required. So this is how we start off for a given test case with frequency array to be 0, all zeros, and before the start of the next test case we kind of reset the frequency array, right? So overall resetting the frequency array overall for a test case is order n1, whatever the number of elements of that test case be. So because the number of test case, like the sum of all ni is bounded by 5a6, and this makes it consistent, uh, the overall complexity of the algorithm will be uh, order n only, right? So we, rather than doing it using map, which would have costed another factor of log n, we removed it by this trick, right? And then finally we report the answer. So this will correctly answer our question. So hope you liked the video. The overall complexity of this problem is order n, and the code that I just showed is an accepted code, so you can go ahead and try to give it a shot. So thank you for your hearing.